This video is going to look at the material shown in figure 6.23, the calculation of the mean and the standard deviation of a discrete numerical variable. The basic assumption behind these calculations is that the visits represented in this video are the entire population of visits, so that the formulas in 6.14 on page 209, that is, formulas for the population values, mu the mean and sigma the standard deviation, apply. So, in thinking about the calculation of the mean and standard deviation, we could think of the data shown here as representing the proportions, for example, of a population of 10,000 women who had these various numbers of visits, 1, 2, 3, 4, and so on. If we thought in terms of 10,000 women, we could look, for example, at 11 visits and see that of 10,000, 68 women had 11 visits. So if we were to consider these data not as proportions but as numbers of actual observations, 68 of those observations would be 11, and 1,702 of those observations would be 5, and 588 of those observations would be 1, and the data would be strung out down an Excel sheet, something like this: 1, 1, 1, 1, 1, and there would be 588 of those, and then 2, 2, 2, 2, 2, and there would be 1,104 of those, and then 3, 3, 3, and so on, 1,710 of those, so that we would have 10,000 cells filled with numbers in these proportions. Then we could simply say that we wanted the average of all 10,000 cells, or we wanted the standard deviation of all 10,000 cells, and we would get an answer with which we are familiar. But now let's look at how we do this, how we get the mean and standard deviation simply with these values and these proportions. And this works only for a discrete numerical variable. By discrete, we mean a variable that takes on values 1, 2, 3, and so on, but does not take on a value such as 1.7 or 2.3 or 8.59. So, before proceeding, I'm going to insert a row and call this P of X, that is the probability of seeing this observation, and this is X. So here, in order to calculate the mean, I want the value times the probability of that value, which will go here. The first value is 1 multiplied times 0.05 is this, equal the first value of X times the probability of X. And when I hit enter, I get 0.058. Now I will simply copy this all the way down, and each one of these represents the number of visits times the probability of those visits, or X times the probability of X. Here I will sum those, following the formula from mu in 6.14 on 209, and this is equal to the sum of these values, and we find that the mean number of visits is 4.7. Now, what about the standard deviation? The standard deviation is given by the second formula in 6.14 on 209. The label we will give that is x minus mu, and mu in this case is this value here, raised to the second power times the probability of x. That's our label. So here I will take x minus mu equal this value, that is x, minus mu, and we will fix that with an F4 because we will always be using the same value for mu, raised to the second power times the probability of x. And when I hit enter, I get 0.74. Now if I click this all the way down, and if we note the formula, it says that we want the sum of these values. So again, I will sum these. I'll just drag that across, and I get 5.07 as the sum. Now this is not the standard deviation, this is the variance. In order to get the standard deviation, I have to say equal SQRT of this. And there is the standard deviation. So we now have the mean and the standard deviation of a discrete numerical variable given only the proportions at which those values of the variable appear. Just incidentally, I used SQRT to get the square root of the variance. I could just as well have used equal the value of the variance raised to a power. And if I want the square root, that is the power of 1 divided by 2. And I get exactly the same value. So either the square root function or raising a value to the power of 1/2 will give the square root.